I was really surprised to find out whether the derivative of the function below exists, and you're going to want to stick around because I promise you that it's not what you think. Given f of x equals x times the absolute value of x, we want to know specifically what happens at the origin. Does the derivative exist and what the value happens to be? Okay, let's step back for a second and look at the simpler version of this. What if it was just f of x equals the absolute value of x? Well, we know graphically that looks like a v and it's continuous everywhere, but its derivative function is continuous everywhere except the origin. See, you can't really draw a single tangent line for a v. You have a cusp there, right? But what happens when you now multiply this function by x as we see in this problem? Does that suddenly make the derivative function continuous everywhere? Okay, well, you can step forward if you want, if you've already seen the product rule, because that's how I'm going to find the derivative of f here. I'm going to let the left side, this x, be called g of x, and the right side will be the absolute value of x. And with the product rule, what it's telling us is to find the derivative, you take the derivative of the left side g times the original h of x, and then you add it to the reverse, where you take the original g this time times the derivative of h. And we know the derivative of x is the simpler one because for g of x, its derivative is going to be 1. So I'm going to plug that in for the left expression here times h of x, giving you absolute value of x. But it's not so simple what the derivative of the absolute value of x happens to be. And maybe many of you have missed this on your exam. So for this one, I'm going to leave the notation as is with this d over dx and stick around so you don't miss this on your next exam. Whenever I see the absolute value of x, I always want to think of a piecewise function way of looking at it, specifically breaking up the domain into two parts, when x is not negative and when it's strictly negative. So when x is greater than or equal to 0, we can say that the absolute value of x is going to be no different than the original x, because if you're taking the absolute value of something that's not negative, you always get the same thing back, right? Okay, now when x is strictly negative, say plugging in a value of -3, for example, which I recommend you can always plug in a value as a test to make sure you're doing this right, you'll get the opposite. You'll get the positive version of the value, right? So we know, though, that because x is strictly negative, we can just drop the absolute value in this case as well and treat it as basically saying take the original x and multiply it by a -1. So this allows us to then take the derivative above and simplify it by breaking it into two parts, where now for the first part, whenever x is strictly not negative, what I can definitively say is that, okay, in this expression, anywhere you see an absolute value of x, I'm going to just replace it with x itself because the absolute value wouldn't change anyhow. That'll give you x plus x times the derivative of this inner function x with respect to x. And we know the derivative of that inner function is 1. So you're going to be just adding x and x, and that will give you 2x. Now we're going to repeat this for the other part of the derivative function for the case where x is strictly negative. So as we saw above, what this means is wherever you see an absolute value sign here, just simply replace that with -x. Now, the derivative of this inner function -x, this time will be a -1. So when you simplify things further, you'll get -x plus x times in parentheses -1, yielding you a result of -2x. So what I like to do now is bring the parts together and represent the derivative function here as a piecewise function. So the top half is going to represent cases where x is not negative, and the bottom half is going to be strictly negative values. Now, remember we talked about the original function, if it were to be the simpler case, y equals absolute value of x, the derivative function is not continuous at the origin. And that's a key word, because when we're trying to find out whether the derivative here of this function, x times the absolute value of x, exists for x equals 0, we need to find out if this derivative function is continuous at the origin as well. And I've got a video you can check out above if you want more help on this. But ultimately what we're going to do here is we want to look at approaching the origin here from the right and the left using limits. And the idea is, okay, if they both give me a defined value and that happens to be the same value in both cases, then we can definitively say that the derivative actually does exist at the origin. So let's approach the origin from the right. I'm going to use this plus sign here to indicate that we're going to have a value of x that's a little positive, like 0.0001, let's just say. So when you're dealing with a slightly positive value, then in this piecewise expression, we're dealing with this 2x part. But you know what? It doesn't really matter because whether it's 2x or negative 2x, the limit of a line here, we're not dividing by 0, so we can just safely plug in 0. And we're going to find that this limit just approaches 0. And similarly, for the bottom half of that piecewise function, this negative 2x, whenever we're using now a very slightly negative value of x, like say negative 0.001, because we're approaching the origin just to the left of 0. Now we're dealing with the negative 2x part of this piecewise function above. And in this case, we just simply get 0 as well by inspection. So what does that tell us? That tells us that because both limits gave us the same value, then clearly for x times the absolute value of x, the derivative happens to exist at the origin and it's a value of 0. And if you want to show this graphically as well, drop me a comment below and tell me how you would do it.